who's a professor at the he's a
I'll
professor
tell
at,
you later.
sorry, it's switching context. So Christoph is a professor at the Institute of Science and Technology Austria, the IST Austria. He received his PhD from the University of Bonn in 2003, and then was a postdoc at the German Research Center for Artificial Intelligence and the Max Planck Institute for Biological Cybernetics. So then in 2010, he joined IST Austria, where since 2015, he's a full professor. He's also the head of the Alice unit at IST Austria. His research interests include machine learning and computer vision, and he has been awarded an ERC starting grant for his research on the interface between machine learning and computer vision. And today he will be talking about learning robustly from multiple sources. We're very much looking forward to your talk.
Thank you. Let me try to share the screen. Okay. Does everyone can see that?
Yes.
Okay, thank you. So the topic of my talk is robust learning from multiple sources. And as introduced, I come to you from IST Austria. So in case you haven't heard about IST Austria, we are a public research institute located close to Vienna, and we work on curiosity-driven interdisciplinary research in all natural and mathematical sciences, computer science, math, physics, chemistry, neuroscience, and biology. And I'm telling you that because we're still hiring, so we're looking for everybody from interns, PhD student, postdocs, up to faculty and tenure track or tenured. If you want to know more, just send me an email or check out the webpage. So my own group is located at the interface between machine learning and computer vision. We work on a variety of topics from machine learning theory, in particular transfer learning, lifelong learning, the theory of deep learning, over models and algorithms for learning, such as zero-shot learning or continual learning, learning with weak supervision. And we use it for applications in computer vision, such as scene understanding, generative models, or abstract reasoning. So the topic I would like to tell you about today falls into the theory and algorithm section, and it is on trustworthy or robust learning. So what do I mean by that? I will, just to give you a quick overview, I will start with a brief introduction, what I mean. I will then give you a refresher of what we mean by learning, and then talk about learning from untrusted sources in general. The slides are available on my homepage, just so you don't have to write everything down while you listen. Learning from untrusted sources is a big issue in these times. So a lot of the data that machine learning methods build on comes from untrusted sources. So think of any data set that you recently worked with, such as ImageNet. Even if you collected the images yourself, which probably you didn't, the labels were typically created by a process where more or less random people just annotate data, and you have to hope that the results of the annotation is more or less the one that you expect. So crowdsourcing services have this kind of nature that a lot of different people contribute to the creation of one big data set. Biology is a big topic at the moment. Biological data is created in labs, and there's many labs out there, and only if all of them would contribute to the common course, we would probably make more progress. But then you get data from multiple labs, and not all of them might follow the same standards. So the moment you have multiple contributing parties, you might have to live with the fact that not all of the data you get is equally trustworthy. So this is a general pattern. You get data often from some kind of online sources, and you don't trust all of them to be exactly what you want. It could even be that some of these sources, I mean, if it's some kind of important task you're trying to solve, then some of these sources might even be compromised. They might be malicious, trying to prevent you from achieving your goal. So imagine that some of the sources that work with are either sloppily annotated or even maliciously perturbed. And the question we're studying is, how much can we learn under this situation? So can we develop learning?
Sorry for interrupting you. Do you want to close the participant window from the Zoom window? We see the participants window from Zoom.
Oh, interesting. Why? Better?
Yes, thanks. Sorry for interrupting.
That should not have happened, but good. So what can you learn if some of the data is either noisy or corrupted or even adversarially manipulated? So we're going to study this on a fundamental level, not for one specific problem, but for the general problem of learning. And we do this in the context of supervised learning. So let me quickly repeat the main concepts there and the main notation that we're going to need. So in the supervised learning setting, it's a classic prediction problem. We are given some kind of inputs, for example, images or strings or vectors, and we're given some kind of outputs that we want to predict. And for simplicity, let's just assume that we have two labels, plus, minus, one, and we want to solve a binary classification task. All of this, of course, carries over to other classes such as regression and multi-class classification and so on. So the connection between the x's and y's is made by some probability distribution that tells you what input-output combinations are likely. And this is a fixed distribution, but it's unknown to the learner. So all we can do is hope that we get data for it. And finally, there's a loss function that measures for any prediction we make y, whether it was a good one or not. And again, for simplicity, we just use 0-1 loss. So when you make a prediction y bar, you check the ground truth was y, and we see if this was the same or not. That's 0-1 loss. So in the abstract, the goal is to find a prediction function f that maps inputs to outputs, which has the smallest number of possible errors on future data, meaning in expectation over the data distribution. So we define this little ER, the error rate, as the probability that on future data X, the classifier F predicts something that isn't the correct label Y. And we want this to be small in order to have found a good classifier. So that's the standard notation for learning. In order to do that, we get data, and the standard setting again is that we get some kind of training set S, which consists of samples from the data distribution, and it should be sampled IID, so independently and with identical distribution. And then we will fix some kind of model class. So for example, the set of all linear classifiers, or the set of all ResNet 50, or the set of any kind of fixed architecture networks. And we will fix a learning algorithm, or we'll look for a learning algorithm L that takes in a training set, so a subset of XY pairs, and it outputs a trained model. So you can think of this as just finding the parameters of the network that we're looking for. So the central question in learning theory is there a good learning algorithm? Meaning one that if you give it enough training data, it will actually, the solution will converge to the best possible within the learning class. So is it possible to learn such that with enough data, you're as good as possible? And the answer is yes. So at least for the models that we care about on a daily basis, such as linear, neural networks, and so on, and you can formalize that, there is a good learning algorithm, and it's in fact sufficient to just minimize the training error. So give enough data, minimizing the training data is just as good as any other strategy of this type. So the learning algorithm takes the training set, it finds the classifier that has the minimum error over the training set, and as long as the data is enough, so overfitting cannot occur, and we get a provably best classifier out of it. So that is very satisfying. This is the reason why everybody of us runs all of our different optimizers on a daily basis, right? So without this result, there would be no point in minimizing the loss over the training set. So what if some of the data is not good? What if some of the data is unreliable or even malicious? So we can say that we still have a training set, but the data has issues. So for example, some of the points might not really be samples from the data distribution. There might be sensor problems that the data is overwritten with random noise, or numerical problems. Maybe there's nans or whatever. There might be sloppy annotators. There could be trolls that try to make the system racist. There is annotator bias, right? There is, issues of translation. You can even have adversarial examples in your training set, etc., etc. So all of these are different scenarios, and if you want, you can study them in different settings. The disadvantages, you will get different rules, different algorithms for each possible assumption. If that assumption is violated, you will again have to do some kind of different algorithm. So we want to study this in a more formal setting. In particular, we want to see how can we learn in this situation in general? Should we still minimize training error, or is there some better strategy? And are there general statements that are independent of the exact kind of data problems? So is there statements that are strong enough that they cover all of these and more problems at the same time? So for that, we need a formal definition of what's wrong with the data. And we do that by introducing an adversary. So And adversary is another party, another algorithm that can manipulate the data. So it gets the data set as input, and then it outputs another data set which coincides with most of the data, but some of the points are changed. And we call the fraction of data points that can be changed alpha. So in the end, alpha times m of the points can be set arbitrary by the adversary, and 1 minus alpha times m points must be unchanged. Clearly, if the adversary, if the power is alpha equals 0, nothing is wrong. And if alpha equals 1, then you cannot hope for anything. But at least in the setting where alpha is less than half, one could hope that you can overcome the effect of noisy or malicious data. Now, the learning algorithm still sees the training set, but now the training set that it sees is not the original S, but it's the manipulated S, so A of S, which we call S prime. And then the learning algorithm will just use S prime as it is because it doesn't know which data has been manipulated, right? If it knew what was manipulated, it would just throw away the manipulated data, learn on the rest. But it doesn't know what has been manipulated. So it just has to do its thing. It processes the training set, and then it outputs a trained model. And the question is, if the learning algorithm minimizes the training error, will this still be a good learning strategy? Or do we need something else? And unfortunately, the result is no. So if you just minimize training error across a training set in which a certain fraction of points can be manipulated, then no algorithm can guarantee that the error is less than a constant. And the constant is actually this alpha fraction divided by 1 minus alpha. And that is not negligible, as you'll see in the following. So now let's go back to the setting of multiple sources, right? So in the multiple source setting, we're getting data from many different sources. And ideally, they all come from the same data distribution. And then it turns out people don't think much about learning algorithms because the naive strategy of just taking all the data and merging it and then minimizing the training error is guaranteed to work and it's optimal. So there's no point in doing something fancy if the easy thing is already optimal. But now if some of the sources are not reliable and we still follow the strategy, we take all the data and we throw it together, what guarantees do we get? And then the previous result tells us not a lot. So in this setting where 2 of the 5 sources would be malicious, this alpha divided by 1 minus alpha tells us that the naive strategy of throwing all the data together will be even worse than random guessing. There's situations where this will have an error rate of at least 66%, where random guessing might be 50% or something. And even if a smaller fraction is malicious, like just 1 out of 10 sources, the error would still be above 11%. So we're definitely not going to win the ImageNet challenge with that, right? So it's still pretty bad, even if a relatively small fraction of the sources can be manipulated or it's just noisy. So is there a better algorithm? Is there even a universal one? Well, that is the topic of some work we recently did. So this is mainly work by my student Nikola Konstantinov and Elias Franta, who was an intern at that time, and our colleague Dan Alistair at IST. So this was published first at ICML 2019, and then an updated version with stronger adversary at ICML 20. So let's again look at the setting. We have multiple training sets now, S1 to Sn. Each of them is sampled from the true distribution, as it should be. And the multiple source learning algorithm takes in all of these training sets, and it outputs one hypothesis, one trained model from all the data. Now, in the adversarial setting with malicious data, we have an adversary again, and this gets as input all the training sets and outputs a new set of training sets. And some of the training sets are identical to before, and some of them can be arbitrarily manipulated. And again, we call the fraction alpha that can be manipulated. So alpha times capital N is the number of sources that can change, and 1 minus alpha capital N is the ones that stay the same. Again, the learning algorithm doesn't know, of course, which one are manipulated and which one are the originals. Now, this is a powerful adversary. It can look at all the data, and then it can selectively choose which sources, for example, to perturb, or at least it can tailor its manipulations to the available data. And we also assume that it knows the training algorithm just because, typically when you want some kind of security guarantees, you shouldn't keep stuff secret. So it might be known what the training algorithm is. The adversary has that information. Technically, in the paper, we look at 2 variants, one where the adversary picks himself which part of the data sets to manipulate, and some where the subset is fixed, which ones it is, but the actual data content is arbitrary. But this gives you just minor differences in the results. Okay, so the question is there now a universal algorithm such that when you apply the learning algorithm to the manipulated sources and you check the error of the resulting, as long as the number of data points goes to infinity, do we converge to the best possible hypothesis in this setting, as if all the manipulations had not happened? Before I come to the answer, let me say a few words about related work. So we already saw that if you have only a single data set, robust learning is not possible. So there is no algorithm that can guarantee a minimum error less than 1/1 minus alpha. Now, if our data sets have each of them only 1 point, small m equals 1, then this is the same situation, right? Each data set is a point. So a certain fraction of the data sources is manipulated means a certain fraction of the data points is manipulated. So then the same impossibility result holds. And that means that just keeping the number of samples at 1 or fixed number while sending the number of sources to infinity will not be enough to learn arbitrarily well. So we cannot hope to benefit just because we get more and more sources. But we can still hope that if the number of sources stays fixed and we collect more data in them, then this will allow optimal learnability. There's related work in many areas. So for example, in collaborative or federated learning, there's multiple parties that all try to learn one model, but they learn one model for each party. And then you can actually show that learning is possible in that setting. There's density estimation, which is like the unsupervised version of our problem. So that also is possible, but since there's not the concept of labels and prediction functions, it's not the same setting as ours, so you cannot carry over the results easily. And finally, there's the task of Byzantine or robust optimization, where you have a bunch of distributed machines that try to compute, for example, a solution to a neural network that try to minimize some kind of loss. But then some of the machines might be compromised and they might give out no gradients or wrong gradients or manipulated gradients. And the works in this area concentrate on convergence analysis, under which assumptions you still converge, and under assumptions your gradient optimization will not converge at all. So that said, here's our result. There is actually a universal learning algorithm in this setting. So there's an algorithm that if you train on the manipulated sources, as long as the adversary has power less than 1/2, the difference between the error or the loss on this learned hypothesis and the best possible one in this class, so like the best possible setting of all your parameters, is bounded by a certain term, and I'll discuss the term later. But the main point is that this term will converge to 0 if the number of data points goes to infinity. Meaning if you just see enough data, then you will actually get as close to optimal as possible. So you might wonder, why is that the case? So why is it easier to learn from multiple sources than from a single source? And the answer, I would say, is it's actually not easier. But the task for the adversary is harder. If you have a single source, there's no restriction how the adversary can manipulate the data. It can pick any points at once and any possible values for them. In the multiport setting, if it's only possible to manipulate some of the sources, then the manipulations have to adhere to the source structure. So for example, you cannot manipulate each data set a tiny bit. You can manipulate a certain fraction a lot, or you can manipulate a certain fraction a little, but you cannot manipulate everything by a tiny bit. And we can then build an algorithm that exploits the law of large numbers. So we know that the majority of data sets will be, identically distributed from some distribution. So if we see more and more data from these data sets, they should look more and more similar because they converge to the same underlying distribution. So that means we should be identical to identify at least the unperturbed data sets. Maybe there's others that look the same or similar, but at least the unperturbed ones we should be able to find. So this is some kind of filtering idea. And this is what's behind the algorithm that we proposed. So we have the first step in which we identify which sources to trust. So first we compute all pairwise distances between the data sets using a distance measure that I'll tell you about in a second. And then for any possible of the sources for any data set, we check if it is similar to at least half of all available sources by a certain threshold that I don't discuss here. So if a data set is similar to at least half of the others, that means it cannot be similar to just manipulated ones, right? Because the adversary cannot manipulate half the data. It can only manipulate slightly less than half of the data. So if it's at least similar to at least half of all data sets, then it looks reliable, and we include it into the set of reliable ones, T. And then at the end of this process, we create a new data set that merges the data from all the reliable sources, and we minimize the training set over this new merged data set. And the only open choices here are the threshold that I'm not going to talk about and the distance measure. So let me visualize the process. So this is a very abstract view of task space. Each of these little dots of these circles is a task. Now, if all of them are clean, they are all clustered together. And just because of sampling with finite data, they are slightly different from each other. Now, if for any of them, we measure the distance to all the others, and then we threshold them at the given threshold, and we count how many of the others is it similar to. Well, in this case, it's similar to 5 of the others. That's enough. So we include it in the trusted set. Another data set, we compare the distance to all the others. We check the threshold. Again, it's similar to 5 here. That's more than 4. So we can keep it, and so on. So if we do this for all of them, when all data sets are sampled from the same distribution, they will all be included. And actually, all the data entered the trusted set. And we are doing just the same as for the optimal naive algorithm, of meaning throwing all the data together. So if there is no perturbations, we don't lose anything. It's not that we throw away data if we don't have to. What if something is manipulated, then what? So here's a few data sets that look manipulated. So now if we compare are they similar enough to many of the others? The answer is no. And in the end, the algorithm will just select the ones in the middle as reliable. Now here, all the manipulated looks different, but even if they all look similar, in order to try to be consistent to each other, the check for at least half of them to be close means that the manipulated ones cannot support each other enough, but only the unmanipulated ones will enter the learning. One thing that can happen is that the manipulated data sets actually are designed to look extremely similar to the original data sets. So here, they are kind of really close to each other. And then the algorithm will say, well, all of them look similar, and it will include all of them. So it's possible that not just the clean data set, but also some manipulated data sets will enter this so-called trusted subset. And this puts some constraints on the distance measure that we're going to use. So what properties does it have to have? Well, first of all, if 2 data sets come from the same distribution, then the distance should be small, at least if enough samples are available. And that means that given enough data, the clean data sets will eventually be all grouped together. But at the same time, if the distance is small, then the learning should be affected by this. So learning on 2 data sets which are similar to each other by this distance should give similar classifiers. And that means if you manipulate data sets that are later grouped together, well, it won't hurt the learning process. You can try to come up with a distance measure between point sets, between samples, that has these 2 properties. And it's actually not that easy. So there's a lot of distance measures that do not fill these conditions simultaneously. And particularly if you think geometric stuff between points like average Euclidean distance or Hausdorff distance and so on, it will not have these 2 properties at the same time. You can also think of more probabilistic measures such as Wasserstein distance or Kohlberg-Leibler divergence. And then these will typically not have property 1. Wasserstein distance might actually, but it will take a lot of sample and be very slow to converge. So the one distance that actually has these conditions at the same time and is still efficient to compute, well, in terms of samples at least, is the discrepancy distance. So this is the discrepancy distance. It measures the maximum amount that any classifier in the set that we're looking at can disagree between the 2 sets that we're comparing. So we compare the loss on one training set compared to the loss on the other training set, and then out of all possible classifiers, which one has the biggest difference between the 2. It turns out, instead of maximizing over this difference, you can also just train a classification problem by a trick. So in the binary classification setting, you can compute the discrepancy by creating a new data set and training a classifier, which is you take one of the data sets, you flip its labels, you merge the remaining 2 data sets then, and you try to find a classifier that has a small training error. And if you are able to do that, the discrepancy is big. And if you're not able to do that, the discrepancy is large. So let me visualize that. Here's 2 data sets, blue and orange, which you might think are quite different from each other. So this is the original. Now we flip the labels of the orange one. And then after we did that, we merged the 2 together. And now we check, is there a classifier that has a small error on this data set? As it turns out, yes, there is. So that means the error of the training set is small, meaning the discrepancy was large. Now, here's 2 data sets that look quite similar, and we would imagine that the discrepancy would be small. Again, we do the same thing. We flip the labels of one of them, and then we try to find a classifier for the remaining merged data set. And we'll see that actually it's not possible to find a good classifier in this setting. So all of the classifier have some decent training error, meaning that the discrepancy is rather small. Okay, so discrepancy distance has both of the properties we want. On the one hand, data sets from the same distribution do eventually get grouped together. So the discrepancy converges to 0 if the data sets go to, size of the data sets goes to infinity. At the same time, if data sets are grouped together, then it doesn't hurt the learning. So the setting, like imagine you have a training set as train, which is from the correct distribution. And then there's another set which was manipulated. So it's not sampled from the distribution, but it has a really small discrepancy distance to the training set. And then you say, well, if I train on this, and then I compare the result on a test set, how big can the difference be? And it turns out you can derive a bound that the error on the test set cannot be bigger than the error on this manipulated set plus 2 terms that are both small. Meaning if you train a classifier now by minimizing the error on S prime, then the test error will also be small. So you have learned a good classifier, even though you trained on manipulated data. So in combination, this is what makes our possible to prove our theorem. And here's the formal form of it. So we have given n training sets of size m, out of which n minus k can be manipulated and k cannot be manipulated. Then we have this ratio of manipulated to total sources alpha. And then if we train our algorithm on these manipulated data sets, then we can prove that the error of this resulting algorithm cannot be bigger than the optimal possible one, plus a term that has two main terms, one which is 1 over square root of km and one with alpha times 1 over square root of m. Both of these go to 0 when the number of samples goes to infinity. So this strategy actually achieves arbitrarily small error when possible. So the 2 terms are actually interpretable. The first one, k times m, is the number of clean samples, where k is the number of data sets which are not manipulated. M is the size, so k times m is the number of actually good samples we have. So then 1 over square root of km is just the normal speed of learning. So the second term is the slowdown due to the manipulations. And you can actually show that a slowdown is unavoidable and that it will have the form of alpha times 1 over square root of m. So this is actually a result that confirms the lower bound up to constant and logarithmic terms, I should say. With that, let me summarize. So learning from multiple unreliable sources is commonplace these days, and maybe we should pay more attention to it instead of just trying to filter the data once and then learn arbitrarily on it. It can be studied formally by introducing an adversary and giving this a special power that hopefully is enough to be fought by the learning algorithm. In this specific case, the group structure actually allows statistical learning, even against a strong adversary, where without the group structure, this is not possible. And I didn't talk about one aspect, which is computational efficiency, and that is because we actually don't have an efficient algorithm, we just have an algorithm that needs few samples, but computing the discrepancy for it with guarantees seems to be NP hard. So we have a statistical algorithm, but it's not computationally efficient yet. So with that, let me thank my group and my collaborators, in particular Nico, who did most of the work, Dan and Elias, who worked on this work as well, my funding sources, IST itself, and the ERC. And I hope we have time for a few questions. Thank you.
Thank you very much for the very interesting talk. We actually have a couple of questions in the Discord. So one is, there is a separate field of work on privacy preserving machine learning, where data samples are anonymized or perturbed. For example, differential privacy uses perturbations sampled from Laplacian distributions.
Sure.
Would your robust multi-source learning algorithm be also effective in these anonymized / perturbed datasets?
I mean, this is the opposite question, right? So if you give me an anonymized data set, it will still, this is really the other question, right? So we are asking, if a data set is manipulated, but not all of them, can we still learn something on it? And the differential privacy, for example, says, well, we want to be able to learn on something. So the differential privacy is constructed such that you can learn. But at the same time, we want to hide as much other information, such as if an individual is present or not. So I don't think that, both are applicable at the same time, but there's no direct interaction between them.
The other thing was, not formulated a question, but I think there is a question behind, which is it sounds very similar to statistical adversarial defense. Do you see connections there?
You mean defending against adversarial examples by random perturbation, or what?
Yes, I guess so.
I wouldn't say that it's the same, because that is at test time, right? So you have learned one classifier, and then you want to defend against adversarial example, and it turns out a single classifier is prone to attacks. Whereas if you do multiple random perturbations, then you are kind of protected by the law of large numbers somehow. I mean, both of them are applications of randomization in some sense, but it's different because ours really studies the training situation. The output is one fixed classifier. So if you want, this classifier will be susceptible to adversarial examples afterwards as any other. So again, I think it's a different angle of security.
You mentioned that you can't show that there's an efficient algorithm. Do you have an idea of what your algorithm currently would require in terms of time in practical situations?
Well, in practical situation, you would run the algorithm, but not with the guarantee. So we have run the algorithm, of course, and it works. But the guarantee is if you compute the exact discrepancy, and that is computationally hard because it requires minimizing a 0-1 loss. And that's just known to be NP hard. But of course, you can relax it as any other learning problem, and then you minimize, I don't know, log loss or something else, cross entropy. And the guarantees of the theorem don't hold anymore because one is an upper bound and the other is a lower bound, so they don't really cancel out anymore. It still works, right? But you don't have the theoretical guarantees. And it might actually not be, it might be provable that you cannot have efficient efficient computation and sample efficient learning at the same time. So it might be possible that there is some kind of dichotomy here.
I see. There's another question, which is why are Wasserstein and KL divergences unsuitable? In which way precisely do they fail the requirements?
KL divergence is just not well defined if you have finitely many points, right? So if you're given a set of points and you try to compute the KL divergence with some other set of points, the KL is infinite, unless you make some strong smoothing assumption that you say, well, we're not actually computing on the points, we're doing some kind of smooth density estimation, but then it doesn't apply anymore if the assumptions on the density are not fulfilled, right? So the adversary could easily exploit that if he knows that you're going to use some approximation to KL. Wasserstein distance actually is of the right type. You can prove something. It's just that approximating Wasserstein from finite sample grows exponential with the data dimension. So because essentially you need to search over all continuous functions, or Lipschitz functions, you can show that the number of samples you need in a high dimensional space is like precision to the power dimension. So you really, really, really don't want to do that in practice either.
Okay, thank you very much. There seem to be no further questions. So thank you very much again for the interesting talk.
Thank you.
And with that, we come to the last talk in this session. So our last invited speaker is Karamuza. He's a professor of robotics and perception at the Department of Informatics at the